Hello and welcome to another lecture of classical motion of a single particle. Although we are now discussing very broad domains, okay, like the concept of phase space, okay, the fixed points, concept of fixed points, their stabilities, but at one point we have to again remember that we are doing a course here on the single particle motion. So, finally, we have to get back to the realm of classical mechanics. Okay. So, just since in the last lecture we have elaborately discussed several examples of different types of fixed points, okay, we have actually learned a lot of names: nodes, repellers, attractors, saddle points, stable node, unstable node. Okay. So, here in this lecture we simply pose two very well known equations which can be meaningful for classical mechanics. The first equation is x dot is equal to y and y dot is equal to x. Then I will pose another equation, x dot equal to y and y dot equal to minus x. Okay. So, you see that if now you just think that x and y, they are the phase space coordinates, okay. The point is that for just since this is a 2D phase space, so just bringing a correspondence to classical mechanics, we can say this is actually analogous to 1D motion of a particle. And your x can be actually equal to x itself and y can be equal to v. Okay. And the first actually the very first equation, which is the equation of kinematics, okay, that is x dot is nothing but equal to y, which is v by definition. Okay. That is the definition of velocity, okay. And this is true for all. The second equation, which is the y dot, and actually you know this is the, so this is the velocity part. Now, this is the dynamics part, okay, for classical mechanics, because y is the velocity. So, y dot is nothing but the acceleration part, and that is in one case is equal to plus the position coordinate, and here this is exactly equal to the minus of the position coordinate. Of course, you can do the total treatment using some arbitrary constants, non-zero constants, but here for the sake of simplicity, to just convey the essential message of the treatment, I have just considered everything to be 1 here, all the coefficients, all the multiplicative coefficients. Okay. Now, the first point is that we can easily understand this system is very well known to us, okay, because if you simply do x double dot, that will be y dot and that is your minus x. So, you know x double dot plus x is equal to 0, and this is an equation of a simple harmonic oscillator. Okay. On the other hand, if you do this one, you do x double dot, that will be y dot, that is x, and that will give you actually x double dot minus x is equal to 0. Okay. That is something, some motion with damping, okay, and you know the solution of them. Okay. In this one, the solution x as a function of t is given by, okay, a e to the power I omega t. I mean, they are just the cosinus and sinus type of functions, okay, and you can also write in terms of this complex variables. So, a e to the power I omega t plus b e to the power minus I omega t. Okay. Here you can simply write x as a function of t is equal to a e to the power omega t plus b e to the power minus omega t. Now, this omega, okay, should come here as omega square. Since this is 1, actually I forget everything here and I also forget this from this. Okay. So, this omega is 1 here. Okay. So, you can actually write for your case this is equal to a e to the power I t plus b e to the power minus I t. Okay. Then you will have a e to the power t plus b e to the power minus t. This is oscillatory solution, this is exponentially decaying or exponentially growing solution, okay, that we know. Now, we want to know that what are the fixed points. So, both for this the fixed point is the fixed point is 0 0, okay. Here also the fixed point is 0 0, okay. Now, already we have shown in some of the lectures, okay, that in the phase space, okay, these equations leads to the equation of an ellipse. So, an ellipse in the phase space and this gives you a hyperbola in the phase space. Now, we will try to somehow keep that knowledge now a little bit aside and we will simply try to use our matrix method, that is the method with the coefficient matrix, to conclude about the nature of this fixed point. Okay. And we actually also saw that whenever you have a system where the equations, okay, are like this or like this in the vicinity or in the neighborhood of a fixed point, okay, even in a nonlinear system you will actually in the neighborhood of those fixed point you can have respectively a hyperbola or an ellipse. Okay. Now, here for this case what is the coefficient matrix? I use another color A. Okay. So, that will now be 0 1 1 0, okay, from this one. And what will be the coefficient matrix for this? That will be 0 1 minus 1 0. Okay. So, if lambda 1 and lambda 2 are two eigenvalues, so for this case it will have 0 sum and their product will be, so 0 minus 1, so that will be minus 1. Okay. So, lambda 1 will be equal to minus 1 by lambda 2 and lambda 1 is also minus lambda 2. So, minus lambda 2 is equal to minus 1 by lambda 2. So, it means lambda 2 square is equal to 1. So, lambda 2 is equal to plus minus 1, and if lambda 2 is equal to plus minus 1, then lambda 1 is equal to minus plus 1, okay, okay, because of this relation and this relation as well. Okay. So, the first point is that here the fixed point is not a node because the two eigenvalues are not carrying the same sign. Second point is that they are equal in magnitude. Okay. Now, what will be the nature? So, for that you have to draw the hyperbola, and actually when you draw the hyperbola as we have already drawn, you will actually now understand that if you remember that in the x and v plane, which is actually equivalent to y here, okay, we have this type of hyperbola. Okay. And so, actually you will see that if the hyperbola are like this or like this, okay. So, basically what happens that you will always see that this type of thing. So, you will also have a class of hyperbola like this, I can also draw. Okay. Okay. So, whereas here in this case you will see that the hyperbola they are actually trying to reach from this point. Okay. So, you will see that the hyperbola can be like this, okay, and like this. I do not know whether, yeah, and like this. Okay. So, here you can also show that this hyperbola for those type of thing, okay, in one direction you will actually can have an attractor type of behavior, and for the other direction you will have a repeller type of behavior, and how it comes that I leave to you to decide. So, for example, I am telling you, here you see this type of mixed behavior is not very evident. For that, first of all you have to find the equation of the hyperbola, and you have to draw them properly, and you have to draw the proper directions. Okay. Then you will see that in some cases, in some directions you will have an hyperbola which looks like the repeller. Okay. I mean phase trajectory is a repeller, and in some cases they act as attractor. Okay. So, that is why this type of saddle, I mean fixed point is known as also a saddle point. Okay. Just like the case of another one which we discussed, but here the calling of the saddle point is a little bit subtle. Okay. So, I will actually discuss this point again in the next week more in detail. Okay. But this week what you will try to find the actually to reconcile the fact that if this is a saddle point, then there will be a mixed character of the fixed point which is here in the middle, okay, of an attractor and a repeller. Now, remember here also this fixed point is an isolated point, and no trajectory is actually touch. Okay, I mean no trajectory is actually touching the fixed point. Okay. Finally, to wrap up this well known situation where we have an ellipse and we have 0 0 1 minus 1. So, lambda 1 plus lambda 2 will be equal to 0 again, lambda 1 lambda 2 will be 1. Okay. So, lambda 1 will be equal to minus lambda 2, and that will be exactly equal to 1 by lambda 1 with a minus sign. So, lambda 1 square should be equal to minus 1, and so lambda 1 will be equal to plus minus I, and lambda 2 will be equal to minus plus I. So, this is a case where you have the two eigenvalues again distinct with different signs, but purely imaginary. Okay. And you have an elliptic trajectory in the neighborhood of the fixed point. Okay. Now, the fixed point is again 0 0 here, you know, okay. And whenever we have such type of closed trajectory like this, we call that an orbit. Okay. Now, for an orbit you see that even when the time is actually changing and increasing, okay. So, the orbit does not change, the phase space trajectory is actually bound here. Okay. So, the perturbation is not growing unlimitedly, and that is why this is also in this case is a stable fixed point. This fixed point is a stable fixed point. Okay. And last point is that this is also an isolated fixed point. That means, just think about the case where you have a simple harmonic oscillator with 0 initial kinetic energy and 0 initial potential energy. So, the total mechanical energy will remain 0 throughout the motion and you will have no motion. So, if you start with any ellipse with non-zero semi-major axis and semi-minor axis on this phase space, okay, it will not have 0 energy, and two parts of the energy in this case are positive definite. So, if they are not 0, the sum can never be 0, that is why they can never come here. Only when if you induce some dissipative effect, then only this ellipses can be shrunk and finally come to this point, and once this reaches this point, the evolution stops forever. Okay. With that, I thank you for this week, and in the next week we will actually discuss a more general case of the equations of dynamics with complex eigenvalues and the concept of spirals and then a little bit of concept of limit cycles, okay, along with some interesting conclusions. Thank you very much.